we're going to talk about electrical circuits. And it's important to understand some real basic things about electricity so that you can figure out things on your own. So let's talk about how circuits work. First of all electricity is the flow of electrons. And electrons are, of course, these really, really tiny particles, but there's billions and billions of them flowing through a circuit. And electrons are negatively charged. So they have an electrostatic charge on them that's negative. So if you think about what's happening in a circuit, if I have a supply, this could be, for example, a 9-volt battery, and then whatever I'm connected to it with wires like a light or an amplifier, whatever it is, that's called the load. Then what happens is the battery has a positive terminal and a negative terminal. Because opposites attract, the electrons go towards the positive terminal because the electrons are negatively charged. So the flow of electrons is around in this direction. But that's actually the opposite direction to the flow of electricity. Electricity, we consider it to flow from the positive terminal to the negative terminal. That's the direction of the flow of electricity. Now with alternating current, it's actually changing directions 120 times per second. For half of the 1/20th of a second, it's going in one direction, and then it actually changes and reverses direction. And so, that's one of the things that people get confused about. How does that work? Because, here's the load over here. Am I sending current to it or is current going away from it? It doesn't matter, because all that's happening is you're transferring energy to the load. So, for example, a light is converting electrical energy to light energy. And it doesn't matter which direction the current is flowing, that conversion process is still happening. So that's what we use mostly, is alternating current. And it's kind of funny because we eventually convert it back to direct current. If you look inside of this projector, for example, you plug it into the outlet, it's being fed alternating current, but inside it's converting that back to direct current. And that's how the electronics inside of that work. Now the lamp itself will work on alternating current, but the power supply that's turning the lamp on is actually running on DC, but it converts it back to AC. So there's a lot of conversion going on there. But that's the way alternating current works. Now electricity is kind of ethereal. It's kind of hard to understand because you can't see it. You can't put your, you can't touch it and feel it, right? So this is an area I had, when I was really young, I really had trouble. I really had a desire to figure out how electronics worked because it always puzzled me, if you turn on a radio, there's a person's voice coming out of it. If you turn on the television, there's an image of a person and a voice coming out. How does that work? It was like, it was magic. It was mysterious to me. And so I wanted to figure it out. And so one day when my parents left the house and I was there alone, I went and got one of my dad's old radios. And I decided that if I could open it up and look inside of it, I could figure out how it works. Makes sense, right? So I went out in the garage and I got in his toolbox and I took out the 4 screws that held the chassis on and pulled the chassis off of it so I could get a look inside. And what's inside of a radio? Well, it's a circuit board, a bunch of components, a transistor, some transistors, a speaker, transformers, and that didn't help me figure it out at all. But I decided then, well, if I can look inside of one of those components, then I can figure it out. So I took a pair of pliers, and there was a circuit board that had a bunch of components on it. And I took a resistor. With the pliers, I wiggled it back and forth until it broke off, and I had this single resistor. And I thought, if I can just see inside of that resistor, I'll figure this out. So I put the resistor on the concrete floor in the garage, and I took one of my favorite analyzation tools for electronics. It's a hammer, right? And I broke it open to look inside of it. But inside of it, what's inside of a resistor? Is black carbon powder, And so that didn't help me figure it out either. But years later, when I went to high school, they were offering an electronics course. And I thought, this is my opportunity. I signed up. Now, this was a 2-year class, right? So the first year, half of the class had already had electronics for a whole year. And then the other half was brand new to it. And I was in the park with the brand new, with all the new kids. And the teacher started talking about voltage and current. And to me, it didn't register because to me electricity was electricity. I didn't know the difference between voltage and current until he explained it in this way. He said, electricity is kind of like water. If you have a water system like this, say you've got a big tank of water like a municipal water supply, water tank. And you have the gravity is pressing down on the surface of the water, creating water pressure around the edge of the tank. And then if you've got a pipe in it, the water can go through, it pushes the water through that pipe. And then if you add another pump to increase the water pressure, now you can push the water up higher than the level of the tank. And then if you've got a smaller pipe, that will squeeze off the flow and less water can flow through the pipe. So an electrical system is very similar to that in the sense that you have the electrical current going through the conductors. Instead of a pipe, it's a copper conductor or some conductive material. And the water pressure is like voltage. So the voltage is like electrical pressure, and the flow of water is like electrical current. And so now it made a lot more sense to me. So if you think about, when you when you plug a light in, the outlet is supplying the pressure, the electrical pressure or the voltage. And to measure that, you use a voltmeter. You can measure the voltage on a circuit with a voltmeter. And then the amount of current that goes through the light or whatever you plug in, you can measure that with an ammeter. It clamps on around one of the conductors so it measures the magnetic field, which is proportional to the amount of current flowing through it, and you can tell how much current is flowing through that circuit. Now, there are certain rules or laws of the way circuits work. So let's talk about electrical circuits, and there's just a few basic laws of nature, laws of physics that apply here. So first of all, electrical current always tries to get back to its source. Where did it come from? So you have, and now I've drawn this is what's called a schematic diagram, which shows the supply right here, and this squiggly line means that it's alternating current. And then this zigzag over here, that's the symbol for a resistor, but that represents any load, anything you plug in. It could be an amplifier, it could be a video projector, it could be a moving light, it can be a static light, whatever it is, we're plugging it in. And so the way it works is the current leaves the supply, it goes through the circuit, through the load, and back to the supply again. So it doesn't care about going off anywhere else. If I have another piece of wire that comes off of this and stops right here, and if I were to then, say for example, a bird were to land on this wire right here, then the bird wouldn't get shocked because the current doesn't want to come out here, it wants to go back to the supply. So current only cares about going back to from where it started, to the supply. And typically, the kind of shows we do, the supply is going to be a feeder transformer. If you were to walk around this building, you would see a big giant transformer that is supplying power to this building. Or in some cases, if you're doing a show out in a cornfield, or you're doing a street fair, or a street concert, you might have a portable power generator. That's the supply. If you walk outside and there's lightning, what's the supply? Lightning is electricity, it's current. So what's the source of that? Well, you have clouds and you have the earth. And if you think about the earth and the atmosphere around it, that's the supply. The cloud is like the positive terminal, the earth is like the negative terminal. So lightning wants to go from positive to negative. It doesn't care about anything else. If you're driving around in your car and your car is insulated from the earth on the rubber tires, chances are lightning's not going to strike your car because it's not connected to the earth. It wants to get back to its source where it came from, which is the earth. Yeah, Kevin? Oh, you're good? Okay. So that's the first thing to know. Current only cares about going back to its source. Now, in order for any current to flow at all, there has to be a complete path from the supply through the circuit back to the supply again. If there are any breaks in the circuit, then no current can flow. That's what some people call a high impedance air gap, or it's been air gapped. You know, if you unplug something, you're air gapping it. You put a gap of air, and air is not conductive normally, except when lightning strikes, right? So air can be conductive, but normally it's not. So in order for any current at all, there has to be a complete path. So that's the other thing you need to know about circuits. Then, how many people here have ever heard this phrase before? Current takes the path of least resistance. You heard that? Yeah. How many people think it's true? How many people think it's not true? Good. How many don't know? Okay. So, you know, that's a phrase that a lot of electricians use. Current takes the path of least resistance. Well, let's look at a typical circuit, which would be, here's my transformer, that's my supply. Now I've drawn a symbol for a transformer, which is a bunch of half circles. You know, there's two, these are coils of wire back to back. And this generates voltage, and then we've got, if you were to look at any outlet, if you were to take the cover off of an outlet, what you would find is 3 wires. What color are those wires in the United States? Black, white, and green. So the black is the hot. That's what has the voltage on it. The white is called the neutral. And the neutral is connected to, back at the supply, so this would be the hot, this would be the neutral. I can't draw it white because it's on a white background, but this is the neutral. And notice, and here's the green grounding conductor. Notice that back at the supply, you see how the neutral and the green grounding conductor are connected together? That's really important. So at the supply, the neutral and the grounding conductor are what are called bonded. They're connected together. So the reason for that is the green grounding conductor is connected to the chassis, the metal parts of the electrical system. You can see this dashed line right here. That represents the metal junction box or the chassis of whatever that is. Say it's an audio amplifier. Then the green wire, if you were to open the amplifier and look at where that green wire connects inside of the amplifier, it connects to the chassis, the metal bits inside of that device. That's there in case there's what's called a fault. A fault is a short to the chassis or to another piece of wire. So if there's a fault, and that's what I'm showing right here, this wire's broken, so the neutral is no longer connected, but the hot is connected to the metal part. That energizes that piece of metal, the chassis. It's made at 120 volts. So the green wire is here in case this happens. Then it creates a dead short because it connects back to the supply, and we want it to be a dead short in order to trip this circuit breaker. Because if there's a dead short, a lot of current's going to flow and the circuit breaker will turn off. That's the way we build our electrical systems in North America, in the United States. So suppose there's a fault like this, and current's going to flow through the hot conductor, through the metal chassis, through the green grounding conductor back to the supply and trip that circuit breaker. But what if this person happened to be touching that piece of metal at the same time there was a fault? So now, if the person is touching it, there's another path that goes through the hot conductor, through the metal, through the person, through the earth, back to the supply, because this is the grounding rod. You know, every electrical system has a grounding electrode. A lot of times it's a rod that's driven into the ground that's connected to the green wire. So there's another path, and you can't see it very well, but this is the earth right here. So there is a path through the earth, through the grounding rod, back to the supply again. So if he's touching it at the same time there's a fault, there's actually 2 paths for fault current. One is through the green conductor, the other is through that person. So will that person get shocked if he's touching that piece of metal at the same time there's a fault? You think so? Well, let's watch. So here comes our person, and he touches it. So now, there's a you can see the fault current going through the green wire, and it goes through the person. So which has the path of least resistance? Is it the copper wire or is it the person? The copper wire does. Copper wire has almost no resistance in it. A person, as we saw earlier, has a lot of resistance. A person could have 1,000,000 ohms of resistance, right? But the person still gets shocked. So it's not true that current takes the path of least resistance. What's true is that current takes every available path that it has, but it is true that it divides in proportion to the amount of resistance. It divides in proportion to the amount of resistance. Do you have a question? Or?
Yeah, that's what you're trying to do. Shows that saying that what were you saying right now?
The current takes the path of least
resistance is wrong, but to say the current will take as many paths or circuits are available and it will distribute the energy is correct to say.
Exactly. Yeah. So it divides in proportion.
The height that electricity will take the path of least resistance, and that you'll be okay touching something.
No,
it's get shocked.
Yeah.
And it will go, and it will take the path of least resistance, but you will feel some of that power too.
Yeah. So what you're saying is, he said that I said it's okay to touch things, and
no, it's not okay.
Well,
no, but if you do touch it,
here's what I want you to take away from this.
Yes.
I want you to understand how important, where is it? This green wire is right here. Because if this green wire was not here, then all the current would go through the person. It keeps stopping. And with the green wire, most of the current goes through the green wire, which is what makes it safe. Remember, what are the 5 ways that we said protect you from electricity? Anybody remember? Insulation, isolation, circuit breakers,
grounding,
GFCIs, and grounding. That's why we say grounding is one of the ways that we protect ourselves from electricity, because it will take most of that current away, which allows, if somebody does happen to be touching it, that could save their life. That's the way it's designed. That's the way it's built. That's why we never lift the ground, the safety ground, for any reason. If there are ground loops, there are ways to stop the ground loops without lifting the safety ground. That's how important that green wire is. Does that make sense?
Yes.
Yeah? Everybody see that? Great.
So, quick question. So the circuit breaker, if you didn't have the ground wire, will trip at the same time, but the difference is without the ground wire, more current will go to the individual, right?
Yeah, so let's see, Gabriel, right? Yeah. Gabriel said without the grounding wire, the circuit breaker would trip, but the person would get all the current. Actually, we don't know if the circuit breaker would trip or not, because this circuit breaker, typically that's a 20 amp circuit breaker. That means that more than 20 amps has to flow through the person for that circuit breaker to trip. But depending on how much resistance there is, that may or may not happen. It could be that there's only 1 amp flowing through the person, so that circuit breaker may not ever trip if you're being shocked without that green grounding conductor. That's how important that is. And can 1 amp kill you?
Yes.
Absolutely. Yeah. So it's important that we never take away this green wire, or if you see that it's broken, then it needs to be, that piece of gear needs to be taken out of service and replaced with the proper gear. Okay? Now, here's the last thing we're going to talk about circuits, the way circuits work. Okay, so in any circuit, any circuit is a loop. It's a closed loop. In order for any current to flow, there's got to be a complete path all the way around. And if you add up the voltages around the loop, they will add to 0. And here's how it works. The supply elevates the voltage. It always starts at 0 because we have this grounding electrode that's connected to the earth, like it can be a rod that we pound into the earth. And the copper rod, the grounding electrode, is conductive, so it takes the voltage of the earth. What's the voltage of the earth? Zero. The earth has no voltage, right? It's ground, it's earth. It's by definition 0 volts. So we're forcing this point right here to be at 0 volts when we tie the green grounding conductor to it. And then the supply elevates the voltage. Now in the United States and North America, it elevates it to 120 volts. So at the outlet, if we measure the voltage, it would read 120 volts. Now when we plug in a cable, like an extension cord or a stinger or whatever you want to call it, Sockapex, then there's a black wire and there's a white wire. I'm not showing the green wire, but it's there. But the black wire and the white wire. And then what happens is, as you go around the loop, the voltage drops back to 0 volts. So this black wire is going to drop it a little bit, and then the load will drop it a lot, and then this white wire will drop it the rest of the way back to 0. And how much it drops across the wire depends on how long the wire is and how big the wire is. The bigger the wire, the less resistance, the less it drops the voltage. So when you plug in a cable to supply a load, like a light or something, then you get what's called voltage drop. Okay, so for example, if say you have a 150-foot extension cord with number 14 wire in it. That's a relatively small gauge wire. It has a lot of resistance because there's not a lot of area for the current to flow through it. So it's kind of squeezed, it's like a small pipe, it squeezes off the current. So there's a high resistance. And so that drops the voltage quite a bit. And you've got 150 feet from here to here. You've got another 150 feet from here to here. So you really have 300 feet of small copper wire. So the voltage could drop. That could cause, say, it causes a 10 volts drop in voltage. 5 volts across the black wire and 5 volts across the white wire. So if you start with 120, then how much voltage is going to be at the load itself? Sorry? No, it's 120 minus 10 volts because there's a 10 volt drop. 110 volts. Now in some cases, all that will do, like say for example you're using a par can. All that's going to do is the light will still work, but the color temperature is going to change. It'll look more orange or more brown or yellow instead of white. So if you've got a whole bunch of lights, that's really when a camera sees it. For a camera, the light intensity is important, but also the color of the light. How white is it? Is it kind of bluish white or is it reddish white? There's a whole scale between red and blue. There's also a scale between green and magenta, and there's nothing more unflattering than green light. So when you have an incandescent light, it only goes between red and blue. It does, an incandescent, like a par can, a conventional par can will never look greenish or magenta. But some of the other lights, LEDs and arc lamps, they can get off of that red-blue scale and go into the green area or into the magenta area. And there's ways to fix that. Just like there's color correction to correct between red and blue, there's also what's called minus green correction. So if the light is a bit greenish, you put in some minus green, it makes it more magenta. It brings it back towards what it should look like. So if you have excessive voltage drop, then it could change the color temperature of an incandescent lamp. So that's why you want to make sure you have the right gauge wires if you have a really long run. So one way you can fix this is bigger wire gauge. So instead of number 14, what's the next biggest wire gauge from number 14?
12.
Number 12. So you get a number 12 wire instead of number 14, or you could go to a number 10 if it's a really long run, So, and here's the other problem with excessive voltage drop. If there's too much voltage drop, that means high resistance. And if there's high current and high resistance, the combination of high current and high resistance produces heat. So if you have excessive voltage drop, that cable is going to heat up. Yes?
Do the connections, like if you're putting two feeder cables together, does that add to the resistance? Or
Yes, yeah. The question is, when you make a connection, does it add to the resistance? Absolutely. Because the connection is a friction connection. And depending on how clean the contacts are and how much compression there is and how well they connect together, that can cause too much resistance, and that's usually the point of failure. If you look at, if you've ever seen, how many people here have ever seen a cable fail before from heat? Yeah. Where does it fail first? At the connection. Typically, it gets really hot there. And when it gets too hot, it deteriorates the insulation, and then it either melts or it can short out. There's a number of things it can do, and that's why it's a good idea. If you're doing a concert tour, if you're on a tour, one of the tools you should have is an infrared thermometer. You can point it at some device like a CAM connector or Sockapex connector or even Edison connector, and you start to gauge what the normal operating temperature should be. If it's too hot, then shut it off, replace it. And sorry? It's called an infrared thermometer. You can get an inexpensive one at Home Depot or Lowe's for $35, $45. You can get a very expensive one that has an imaging camera from Fluke for $2,000 or $3,000. The advantage is that instead of having, the inexpensive ones have a laser beam. It's like a little laser that you have to hit the device with the laser to get it to read its temperature. But the imaging ones, you just point it and it'll show you a whole area, and you can see hot spots within that area. So you can just point it at the power distro, the rack where all the power is distributed with the circuit breakers and everything. And if there's one device on there, say you've got 42 circuit breakers on that rack. If there's one that's overheating, you can just point the image, the entire rack, and you'll see the red glow on the image. So it's much faster and more effective. Whereas with the inexpensive one, you'd have to individually look at all 42 of those circuit breakers. So that's a good tool to have. And if you don't happen to have one, you know what else you can do? How about your bare hand? Just go around, feel stuff. You'll see me on shows all the time. I'm walking around feeling conductors, see how hot they are. And after a while, you kind of get a good sense of what normal is and what abnormal is. And I've had a few occasions to feel something go, that's not quite right. And so you replace it when you can at the first available opportunity. And, it's best to do this before the shows, before the downbeat, first downbeat, so you have time to do something about it. And, one of the shows I did in February, the electrician had a thermometer, and he found a bad connector before the first show. And so that, who knows what could have happened if he didn't catch that. So that's what excessive voltage drop can do. Now, excessive voltage drop, the codes and regulations say 3% voltage drop is too much. So how do you figure that out? Well, if you start with 120 volts, what's 3% of 120? Anybody know? Almost 4, 3.6 volts. So what is 120 minus 3.6? It's about 116.4. So if you're at the load and you have a way of measuring the voltage at the, whatever you've got plugged in, you should read at least 116.4 or higher. Now a lot of times there's no place to measure the voltage there, because you need to be able to get to these conductors. So that's why it's a good idea every once in a while to have a twofer. You know what a twofer is? It splits off, so you've got two outlets from one. So one of the twofers you plug in the device, and the other is there for you to measure the voltage while it's operating. And you have to measure it while the thing is on. Otherwise, you will not see the voltage drop. because the voltage drop depends on the amount of current flowing through that conductor. Because remember, it's the combination of current and the resistance that produces the voltage drop. So, you know, a friend of mine worked the Republican National Convention last time, and it was in a big arena, and they had a bunch of follow spots, and they had a 300-foot run of cable. And when he got to the arena, the electricians had already run the cable, and they used very small wire. I think it's number 12 wire, and these were 3,000 watt follow spots. And he looked at it and he said, "That's not going to work. We need bigger gauge wire." And the house electricians there said, "No, it's fine. It'll be okay." And it wasn't okay, because as soon as they turned on the follow spots, then the voltage drop caused the ballasts to overheat. And so as soon as it overheated, the follow spot would shut off. You know, it's got thermal sensors in it. It would shut off the follow spot so it doesn't destroy itself. So his crew would have to run over there and swap out the ballast, the power supply. And as soon as it cooled off, then another one would go out. They'd run over, swap it out, and then another, and another, and they were running all over the arena playing whack-a-mole with these power supplies. And the reason that the house electricians thought it was okay is because they ran the cable 300 feet, and before they plugged in the follow spot and turned it on, they took their meter and measured the voltage at the end of the line. Well, if there's no current, if the lights aren't on, there's no current, there's no voltage drop. So whatever the voltage is at the supply is exactly what you're going to read at the other end of the cable until you turn on the load. So you could literally run a mile of cable and measure the voltage, and you would see no voltage drop at all. And you'd say, "I don't see a problem." Well, there is a problem as soon as you turn on the device. Okay, so voltage drop is something you have to watch out for if you're running cables a long way. So normally you might run a number 12 extension cord, and that's fine for a lot of situations. Or you run, 100 feet of sockapex. But if you have to run 200 feet, that's going to double the voltage drop. Now you have to either calculate it beforehand or measure it on site and be prepared to do something about it. You know, what can you do? How do you fix it? You can either lower the current. So say, for example, you run a sockapex circuit, and sockapex is a multi-conductor cable with we use the 19-pin circular connectors, which, by the way, are not rated or not approved, what's it called? UL listed. They're not listed. So
connector itself is not UL listed?
The connector or the cable is not UL listed. So in some situations you'll find that, like especially in permanent installations, it doesn't go. The inspector will nix it.
Really?
So you need to be aware of that. Anyway, so if you how do you fix it? Well, you can either say, for example, you run sockapex, and then you have the breakouts. That's where you take the 19-pin connector and you have multiple cables coming off of that with Edison plugs on it or whatever connector you have. And then you plug in a twofer off of that, and you plug two lights into one circuit. Right? Well, with LEDs now, that's perfectly reasonable, except if there's too much current, the voltage drop will be too much. So what can you do? You can unplug one of those devices. Now you have the current. Current is half, and now the voltage drop will be half as well. Or you can either go to bigger cable, although it's not often that, typically sockapex is either 14 gauge or 12 gauge. So if you have 14 gauge sockapex, you can go to 12 gauge. But if you're already using 12 gauge, good luck finding sockapex with bigger wire than that, because I don't think it exists. But you've got to either go to bigger wire, or shorter run, or less current. Those are the three ways to resolve excessive voltage drop. So if you've got a big stage or a big platform 100 feet across, like in some instances, and you're going to be running cable a long way, then you need to take into account the potential voltage drop and do something about that. Okay, so that's voltage drop. But that's the way circuits work. Now, Ohm's law is probably the single most important thing that you need to know about electricity. Ohm's law says the voltage is the current times the resistance. Now that works for the entire system. You know, you could go to, say you've got a show on portable power. You can go to the power generator, you can measure the voltage, and you can measure the current because you've got a voltmeter and an amp meter, and with those two values you can calculate the resistance of the entire circuit. Or you can go to an individual device and measure the resistance across, say, a par can or a Lico or whatever. You can measure the resistance across that device, and that'll tell you, say for example, you've got, you know, the voltage, because in the United States it's usually 120 or thereabout. Then you can predict the current. And you know, a lot of what we do is kind of predicting the future. Before we ever connect a light or an amplifier or a fog machine or a video projector, we want to predict how much current it's going to draw. Why? Because that tells you what size cable you need, what size connectors you need, how much supply you need. You know, when you go into a venue or you're building a theater or you're building a church, you need to tell the electrical engineers, well, how much power do we need? And typically the way that's done is you have panels that are called switches that have a certain number of amps. So we usually use three-phase power, so there'll be 3 circuits of X number of amps apiece. So a lot of times it's 400 amps, sometimes it's 200 amps, sometimes it's 100 amps. So it's 100, 200, or 400 amps per phase, per leg, and there's 3 of them. So if it's 400 amps 3-phase, you have a total of 1200 amps. And if you have, say for example, for easy math, 1200 instruments that draw 1 amp apiece, then I need 1200 amps. So you need to predict, because you don't want to have to go to a shop and set everything up, plug it in, turn it all on, and then go around and measure everything. You've got to know from the specs how much power you need without ever plugging in the gear. That's why we need to know this stuff. Okay? So Ohm's law is one of the most basic things that you need to know about electricity. Now, you know, usually we hardly ever deal with this value, the resistance. You know, what's the resistance of a platinum SBX? Or what's the resistance of that light right there? Or of you know, I don't know. I don't really care. What I do care about is how much current will it draw? Well, that's related to the resistance, but it's not a value that we often measure. Usually we're going to the specs for that light to look up the wattage or the current draw. And the wattage inherently tells you the resistance or the impedance of that device. It's built in. But what we do want to know is the general relationship, that the voltage is the current times the resistance, because this is what affects things like when I get shocked, how badly am I going to get injured? Because that's related to the amount of voltage, it's related to the amount of current that flows through my body, and it's related to the resistance of my body. So it's just something that inherently you should know, you should internalize. Also, this has to do with voltage drop. The voltage drop, and you know, I use the term voltage drop, sometimes that throws people off. It still follows Ohm's law. If you put a little d right here, you can make this represent how much voltage is going to drop at the load, and that's going to depend on the current and the resistance of that circuit or that load. So you can see right away that if the current is 0, how much voltage drop is there? None, 0. Because 0 times any number is 0. So this is something that you won't use out in the field, but you need to know, if that makes any sense. And the more you know about electricity, the more you'll realize that how important this is. So you should understand Ohm's law, and there's if you go to my website, this is my website, entertainmentelectricity.com. And then you, across the top on the menu, there's something that says Training Resources. And then if you select that, and then under that there's Ohm's Law Practice, Ohm's Law Practice page. And what this will do is it will ask you to select a voltage, 120 volts, 208, whatever you want to put in there. And then it'll ask you how many problems you want to work. Say 50. You put in 50, and then it'll just start asking you, it'll throw this problem up. If the current is X, what's the resistance? If the resistance is Y, how much current is there? And that's a good way to practice this. And hopefully it will become second nature to you, because then you can figure out, you can start to resolve problems on your own. You can figure out situations that you've never come across before. So this is like one of those foundational learning things that is the key to everything else. That's how important it is. Now, when we talk about power, there's a real simple formula for power. And power is just the voltage times the current. And again, you can measure the voltage with the voltmeter. You can measure the current with an ammeter. So you can calculate the power. Or conversely, and this is probably even more applicable, you go to a manufacturer's website, you go to Elation, and you look up Platinum SBX, and it'll tell you the wattage of that device. And you know the voltage. Most moving lights will work on almost any voltage, from 90 volts or 100 volts in Japan all the way up to 230 volts in Europe, or 240 volts in the UK or in Australia. So, but if you know the wattage and you know the voltage that you're going to use, which you should, that's part of your job, is to, when you advance a show or when you are designing a show, is to figure out what voltage we're going to use. Now you can calculate the current draw. And sometimes the specs will give you the current, other times they don't. But it's important because how many can I put on one 20 amp circuit breaker, for example? Most of the branch circuits, the end circuits, the final circuits. So we have our feeder circuit. Feeder circuits are the big fat cable, feeder cable, and then that connects to a power distribution rack, and the power distribution rack subdivides all of the current into branch circuits, those 20 amp circuits with number 12 wire. That's what all the outlets on the wall here, those are called branch circuits. And that's what we're going to use to plug our loads into. And so we have 20 amps to start with. How do we know how many lights we can connect on that one circuit? Well, you need to know how much current it draws. And I highly recommend that you leave a 20% overhead. Why? Because for room for expansion, room for error, room for, there's all kinds of possibilities. Somebody may come along and say, it'd be great if we had a light right there. Where can we plug it in? Well, let's plug it in here. Well, we've only got, 2.5 amps left on that circuit. Will it fit? That kind of thing. So if you always leave 20% overhead, you never want to drive it too hard, because here's what happens. When you have a lot of current flowing through a conductor, it heats up, right? So say, for example, I like to do these thought experiments. Just think about the way things work. So say you took, say you took an extension cord, right? And you took it home and you went into the kitchen, turned on your oven to about 175 degrees. And you give it about 10 minutes to heat up to temperature. And then after it reaches 175 degrees, you open the oven door, you toss that extension cord into the oven. And then you close the door, you walk away from it for, I don't know, how long is a typical show? 2.5, 3, 4 hours? And you let it bake. You come back 3, 4 hours later, you open the door, get your oven mitts, pull that cable out, and you drop it on the counter, and you let it cool off. Now you come back, I don't know, 20, 30 minutes later, and you feel that extension cord, you feel the jacket and the insulation inside. What's it going to feel like? Brittle. It's going to be brittle because you just baked all the moisture out of it. And if you try to straighten it out, what's it going to do? It's going to crack. And the insulation is going to flake off and just fall off. Now you've got live exposed conductors. Well, guess what? That's what happens every time you put a conductor into service. When current flows through it, it heats up. And it bakes all the elasticity out of it. And eventually, the insulation is just going to fail and start cracking and breaking, and it becomes no good, right? So if you drive your equipment really hard, you're going to end its service life prematurely. So we try to be gentle with the equipment, even if it's not ours, it's just respectful. Try to be gentle with it. One of those ways that we can be gentle with it is by leaving some overhead. We never drive it to 100% of its capacity. We want to leave some reserve. We want to leave about 20% overhead just in case, and just to be good to that piece of gear. So for a 20 amp circuit, that means we really have 16 amps to play with. So how do you know if I've got, say I've got some of these lights, some platinum 5Rs or whatever they are. And so how do I know? How many can I put on a circuit? Well, you go to the manufacturer's specs. The first thing I'm going to look for is I'm going to look for how much current at a certain voltage. So a lot of times they'll tell you that device draws 3.5 amps at 120 volts or whatever that number is, right? Oh, 3.5, okay. So now, if it's 3.5 amps, I can take my calculator out and go, if I want to leave 20% overhead, now I'm going to start with 16 amps. So I'll get my calculator and I'll say, what is 16 divided by 3.5? Well, that's 4.5. So what it's saying is, I can safely put 4 of those lights on a 20 amp circuit. Now, do I necessarily want to do that personally? No. Why? Because what happens if you trip a circuit breaker? If something overheats and the circuit breaker shuts off, now you've lost 4 lights. That's a lot, in my opinion. So personally, really what I'm looking for is, can I put 2 of them on a 20 amp circuit breaker? So what I'm really looking for is, does that light draw more than 8 amps or less than 8 amps? That's the breakover point. So if it's less than 8 amps, I'm going to put 2 on a 20 amp circuit breaker. If it's more than 8 amps, I'm going to put 1. Of course, it still has to be less than 16 or 20 amps. And most of the things we use will not draw more than about 12 amps or so. Now keep in mind, when you first turn it on, if it's an arc lamp, it's going to have a high current until the lamp warms up, and it takes about 5 minutes for it to reach its full operating temperature. So it's going to draw a high current, and over a 5-minute time it's going to drop down to its normal current draw. So if the normal current is 6 amps, it could draw about 9 amps and then drop down to 6 amps over a 5-minute period. Yes?
Is that inrush or is inrush?
Okay, the question is, are you talking about inrush or something else? I'm talking about something else. Now, inrush is what happens when you first turn on a device. There's a big spike of current that drops down really quickly. That happens with incandescent lights, because if you have an incandescent light has a filament, a tungsten filament. That's like a Parcan, the old, conventional light, not an LED, but a conventional Parcan or a Lico. The filament is cold, it's room temperature. So it has a very low resistance. When you turn it on, if there's low resistance, the current is going to be very high. But when the current rushes in, it heats up the filament, which means the resistance of the filament goes up, so the current comes back down. So what happens is, you get this big inrush of current, but within half a second, the current drops back down to its normal current draw. That's inrush. Now, we used to have to only had to worry about inrush with incandescent lamps, which are conventional Parcans, Licos, Fresnels. Now with LEDs have a lot of capacitors in them. And almost anything with a switch mode power supply, which is automated lighting, which is computers, consoles, when you first turn them on, the capacitors have to charge up. So there's an inrush for a different reason. And that's also why a lot of these LED wash fixtures, you know, they may only draw less than 1 amp apiece. So you think to yourself, 1 amp, I can put 16 on a circuit, on a 20 amp circuit, and still have 20% overhead. But if you look at the manufacturers, if you read the user manual, then a lot of times it'll tell you don't put more than 8 on a 20 amp circuit. Why? Because when you first turn on, if you have 16 of them connected on a 20 amp circuit and turn them all on at the same time, you get the inrush for every one, it could trip the circuit breaker. Now personally, just for testing purposes, there's a particular type of LED wash fixture that said you can put 8 on a 20 amp circuit. I put 32 on a 20 amp circuit just for fun. See what would happen? It worked. I wouldn't recommend it, but it worked. And the reason it worked is because I put one on and I would turn it on, and then I would turn the circuit off, and then I'd add another one. Well, I've already turned the first one on, so the capacitors are already charged up. So when I add the second one, the inrush is only charging that second fixture. If I were to connect 32 without ever having turned them on, and then I tried to turn on that circuit, it wouldn't work. So, yes?
Now, when they do the manufacturing specs, are they pretty dead on with their amperage, or do they pad? I mean,
Good question. Okay, so the question is, how accurate are the specs in regards to the current draw? In my experience, it varies quite a bit because of tolerances, and also, a lot of gear is manufactured in places other than the United States, so they have different voltage and different frequency. A lot of times the specs are based on 50 hertz, not 60 hertz, and that does affect the current draw. So what I like to do is I like to keep a database. Every time I do a show, I'm going to measure one fixture, one instrument, and then now I know. And if you'll compare it to what the specs say, a lot of times you'll see the specs or your results vary by 10-15% or more. Also, as the gear ages, the current draw changes. So, it depends on how much cable you have, the condition of the cable, the connector. So there's a lot of variables. And so, again, that's one of the reasons we like to leave that 20% overhead, because you can't account for everything. You've got to leave some room for error. And that's what we do by building in a 20% overhead. Yes?
This might be in the same realm that you asked. When they spec these fixtures, do they put the initial draw to cut it on in the specs with it?
Some manufacturers include the current draw, some only include the wattage. And if you look at the formula for wattage, the watts is equal to the volts times the amps. So if you know the voltage, and you should, then you can calculate the current draw in amps. And so it's almost giving you the same information. But as you'll see, this formula is for DC power. And we almost never use DC. So when we talk about AC power, there's a twist. And we'll talk about that in a moment. But the basic formula for power, for DC power is voltage times the current. And some electricians know this as the West Virginia formula, because if you look at the units of measure, it becomes watts equals volts times amps. So it's an easy way to remember W equals V times A, West Virginia. So that's DC power. And you've got in your books the formula wheel that has all the formulas that you will need. There's 12 different formulas in here. And the way it works is whatever you're looking for, like say you're looking for current, which is often what we're looking for, then you come to this quadrant that has I for current, and there's 3 formulas. So if you know the power, So, say you know the power and the voltage, you can use this formula, which is typically what we're doing. Okay? So that's that. Now, anytime you have current flowing through a conductor, there's a magnetic field around it. Did you know that? So that's important because that's how transformers work. It's also how noise gets into the system. If you have a lot of current flowing through a conductor, like in feeder cable is a big fat cable, if you then run an audio cable next to it, well, don't be surprised if noise gets induced into the audio system because through the magnetic field. The magnetism represents energy, and it can be picked up by any conductor. So that's why when we run audio cable, we run it at right angles to current carrying conductors like feeder cable, because that way the audio cable will slice through in between the lines of flux of the magnetism. We're going to talk about AC, but before we do, why don't we go ahead and take a 10-minute break.